And hello, students. These are some solutions to selected, if not all, of the Chapter 6, first part of this Chapter 6, there, 6A assignment here. And as we already had already done 6.1 in the class, in breakout sessions in Zoom, I'm going to pick up with question 3 here, okay? And the question refers to the same topic as question 1 is how do we sample, okay? So in creating a plan and finding an appropriate sampling technique, we have to have a survey of the different types of techniques. This comes from approximately, I think, page 222 out of the book. Okay, and it says describe how to apply stratified sampling to sample from the accompanying credit risk data based on the different types of loans. So this was the file that you would get. Okay, so in homework, when you click, you'll get this. All right, so there's different things. Your loan purpose, checking savings. I think is how much is in your checking or savings account when you're going for the loan. Months of a customer must be from a bank that they're familiar with these customers. They have a checking savings account, so they're now trying to get a loan. How long have they been employed by month? Gender, marital status, age, housing, job, and then credit risk. If we click on this, there's no kind of formula across here how it was assigned. Okay, so we don't know whether the credit risk here seems to be pretty much the dependent variable on something that do with the rest of these data in here. And they segment, and so these are actually, we can tell that they're already segmented out into credit risk to draw it a different way, like a gauge. All right, so you have this low, medium, and high. Okay, we're probably not even saying anything about it right now because if we think about the banking a little bit, we may want high risk. We might want the high risk people. And what we do is we might be very good at the actuarial tables and such around the high risk people here, and we can figure out how many are going to default, and we set our rates so that these people might need the loans most. They're aware that their credit risk is high or their credit rating is low, and so it doesn't say anything about where this company is going with it. Okay, so I just want to. Usually, I look for extremes in the data. You know, I look to see some kind of conclusion or observation about the data, and be careful about getting trapped into anchoring positions. All right, or sort of maybe even fallacial approaches to this, fallacies about this. So think about it. Open up. There's no constraints here in the problem, and as I keep saying that on these problems, it's the stretch. It's in the imagination of what's going on here that really provides the value. Okay, so what's the business case? What is the business case out of this? It's always the business case for data and how we present it, tell the story. Okay, so that's a really big thing in journalism, even. Okay, so journalism is relating to the course here. Journalism, really in your lifetime converted from, I mean, I think that there would be general agreement that the journalism has decreased in its objectivity. Okay, and now instead of consumers of the journalism of information being able to distinguish what's going on in data, okay, okay, so tables, even graphs are not that good. You'll see in the last 10, 15 years, it has become the story. Okay. And we talk about this as the phenomenon. Okay. Okay. So there's a whole section of research is the phenomenon, trying to explain what is the phenomenon. You have to go in and sometimes entrench yourself inside the community you're studying. Okay. And anyway, I bring this up because I'm stressing that that's what we're doing with this data. Is your job in your careers going forward is going to be convert this into some kind of story. So I'm trying to help out why we could take any one of these problems and turning it into an hour and 25-minute class. Okay, so that's the long story of it, and the way that you should be thinking about all these problems is in a rich way. Match up with the amount of time you have to get these assignments done, but at the same time, try to help you see what's going on. I believe all this data, pretty sure, 99% sure, plus or minus a percent, that all this data was collected over a career by the author. And then this version of the book is actually, I just find that the questions are better. They seem to be tuned in a little bit more. Okay, so how we take data, how we sample has a lot to do with our study. Okay, how are we going to set this thing up? Okay, so the question is describe how to apply They want to know about stratified sampling. They're not saying pick the best sampling technique, but let's go with stratified. So what does stratified mean? Okay, so stratified means you subjectively divide data into groups. Okay, and then what you do is if this is group A, B, and C, okay. So if you add up these populations, there's no overlap here, okay. If you add up the population, you'll get the total population here. You're gonna have the count of A, number of A's, number of B's, number of C's, okay. And I'm going to make a simple problem here. I'm going to say that it was 20. The number of people in this might have been 20,000, and we're just abbreviating it here, but it's like 20, 30, and how boring, and 50, okay? So 20, 30, and 50. That means there's more people in C. So it's 50, B is 30, is 20, okay? And then what we do is we take representative numbers of samples, okay? Our sample size from each of these is going to reflect how big each of these strata are. They don't have to be equal size, okay? So if we go over to our information, do we have anything about that over here? I think you would look at credit risk. Okay, so this is stratified. Let's see how many levels of stratification are unskilled, skilled, management. That's 3 levels here. Own or rent are just 2 different options here. You could stratify them. You could recode some of these numbers, but they're not that great. I mean, years, what is that? Housing years in the housing, I think it is. So it goes up to about 4. These are, people that haven't been in their house for very long. Age, you could stratify that. Okay, so you can recode this. Okay, and you could say, I don't know, I see ages from 23 to I see a 50 in there. I don't know. Let's just say that those are the extremes. You can take 23 through 50 and just create 3 classes there, or 4 classes, and this is what we call recoding the data. Okay, instead of integer ages here, which are rounded, so there's already a little bit of error possibly built into this because we're rounding them. What you can do is build out three strata here that makes sense to your study. Single, divorced, married. That's three here, 2 here. Months employed. So you could recode a couple of these other things. But we already have credit risk, and we believe that's what this problem's about. Okay, so let's go with credit risk because it is a banking problem here. Let's come back here. So what's stratified? Separate the data by gender and select a sample of all females. What that is not stratified. That is somewhat stratified. It sounds like it's stratified, but what that is clustered. Okay, so cluster is when you look for certain common characteristics, right? That's what the cluster is about, and then you grab you can randomly grab the clusters, and you actually that is your sample. Everybody in that cluster is your sample. Okay, so that's if you're going after a certain type within a community, a certain subset within a community. Select a sample of 25 people from the data. Okay, that's not really telling us anything. It doesn't tell us enough to be stratified. This could be anything from just randomly choosing them, all right, all through the one big population, or it could, this could be systematic, where you decide how you're going to go do this and take every X person out of there. Okay. Separate the data by credit risk and select a sample of certain percentage of people from each category of credit risk. That kind of sounds right. Separate the data by credit risk and select a sample of all the people with low credit risk. Nope. We need to have all, for stratified, you have to have all strata represented at the rate that they appear in the population, at the same relative proportion. Okay. So this would be, 0.2. Proportion here is 0.2. Proportion here is 0.3. Proportion here is 0.5. Separate the data by gender and select a sample of all the males. Okay, that's a subset of that. Still not doing it because we're not picking up both females, and we'd have to have males and females in this. Okay, so you'd have if you had 30 males and 70 females, you would take for every 7 females, you would take 3. Okay, so that might be your sample. You'd take a tenth of each of these, but that keeps the proportion between them the same. All right. Select a sample of certain percentage of people. Select a sample of certain percentage of people from the data. Not looking good. No stratification in there. Separate the data by gender. Select a sample of 20 people from. Nope. Nope. We would want to pick. This is still not stratified because we want to pick to the relative proportions that they're represented in the population, and separate the data by credit risk, and select the sample of all the people with high credit risk. See that again is going just it seems to be somewhat repetitive here where they're just going after one of the strata. They're going after high. That's high, medium, and low. Okay, so the answer would be C on that. Okay, so I'm going to walk through problem 6.5 for us here. Now this is just giving us some practice. This problem follows exactly the example in the book. So read the example in the book and then make your connection to what they're doing here. Here, they're going to feed us a few different tables of data depending on the sample size. Okay, so a population that's uniformly distributed. The point that they're making here is the central tendency theorem that this problem speaks to. And again, this is following exactly the problem in the book, so it shouldn't present too much of a uh, mysterious challenge to you. It's a matter of making sure that you do all the steps correctly. And very briefly, I'm going to paraphrase what the book is saying. This is core. It's core to data analytics, core to statistics here. And what's different about what's going on in these problems, you must realize, and hopefully, if you haven't, this explanation will elucidate that a bit. Okay. Now, the idea here is we moved from chapter 4, where we just had populations and samples. And in chapter 4, we had data that was normally distributed. Okay. And we said the mean is sum of all the points divided by n. Okay. I'm going to use a little bit of shorthand here moving through. And the standard deviation is the square root of how far every point is from the mean squared. We sum all those up and then we divide by n. Okay, and when we're all done, we take the square root. Okay, now, so that's the standard deviation of the population. Okay, when we sample, we lose a degree of freedom, is basically what happens. Okay, so the standard deviation of the sample, okay, if we only take one sample, it's going to look like this. It looks almost exactly the same. Every point, see how far it is from the mean. I'm going to draw the mean up there. Squared, and we divide by n minus 1. We lose a degree of freedom, okay? df, or a degree of freedom, okay? What happens is if we don't divide by n minus 1, if we don't subtract the number of 1 from the number of n, we overestimate the variability of the data. That's given to us. We don't derive it. You can derive it if you're a mathematician so inclined, but what it's given to us is that we lose a degree of freedom when we sample. When we take a sample from that, so the standard deviations of a sample of it. So our population might have 20,000 reads in here. Okay, so there's 20,000 readings or uh, items of interest there, and we might sample 20. Okay, so that's the excuse me, that's the difference that between the sampling and the population of a random variable like that. Now, this is the problem of problem 6, and if you didn't realize it because it can get lost in the words. This is crucial to the very core of 6. What's going on now is we take samples. Now remember, a sample could be a reading of 20, and a sample 1, could be a list here. We take 20 readings, 1 through 20, sample 2, okay, 1 through 20, all right? And in chapter 4, when we did normal distribution like this, we were told the data is normally distributed, but in when we do sampling, the central tendency theorem, which is pretty interesting, says they give us this problem here that's the original data isn't even normally distributed. In a way, it doesn't matter what the distribution is like, what kind of distribution you have. So they're trying to prove a point here by saying we have a uniform distribution between I believe it's 10, 0 and 10. Universal, you have to go into the example in the book, and it kind of tells you, yeah, it says A is 0, B is 10, so we have to understand that. And what they're saying is, if the original data is not uniformly distributed, the distribution of the means, okay, what we're talking about here, you have to use very precise words. You have to practice them and kind of memorize them. It's a table of concepts here, is what you're really coming out here. And we're looking at the sample distribution of the mean, okay? And we use these words. It's kind of like akin to where we tried to memorize that the standard deviation of normally distributed data is like the average distance to the mean of all the points. And by memorizing that, we remember the formula, we remember the concept. It's that it's basically the average distance to the mean of all the points. Down here, we're coming up with some new phraseology of sampling, the sample distribution of the mean, the sampling distribution of the mean is what we're after here. And if we keep sampling this uniform distribution, what ends up happening is the more heavily we sample it, the more thoroughly we sample it. It's almost approaching, remember the word census, okay? So a census means it's not sampling, it's sampling of everything. So that's what the word census means in statistics, okay? So what happens is the more points you take, the more pure outcomes that's going to happen. Is what happened is for every one of these readings, these samplings rather, for every one of these samplings, okay, and it could go how many times you sample, right? We calculate the sample 1 mean, okay? We're going to do the sample 1 mean, the sample 2 mean, sample 3 mean. So these are mini samples. And then what we do is we take all of these and we plot them, okay? And what we're told by the central tendency theorem is keep in mind that it's broadly applied because the underlying data doesn't have to be normally distributed. It says the mean of these samples is the mean of the population. Okay, so the sum of all these n's, all of we're going to sum all these up and divide by the number of samples. So if it comes up to sample is equal to 17, I'm trying to use numbers that don't come out of the book so you don't get anchored into the numbers here. Okay, that's what ends up happening when you use the examples too heavily, is that you tend to forget what we can change about this. So this we have 17 samples and the sample size is 20. So it would be 17 times 20 would be 340 readings. Okay, so we could either take more of these samples or we could take more of the size. We can make the size larger in here. And as we take the average of these samples, it will look like the mean of the original data that we have. So we know that the mean of uniform data is just B minus A over 2. It's halfway between the A and B. And here it just happens to be A is 0, so it ends up being that it's 10 over 2 is equal to 5. Okay. So now we can plot the mean of the means. That's the crux of this problem. Make sure you understand that. All right. So then what we could do is, so we're going to plot the mean of the means, and it comes out to be the mean of the population. Okay. Now the variability, this is what we're really interested in. Okay. So the variability of these samples here is equal to the standard deviation of the population divided by how many, it's our sample size here. It's divided by the sample size. Okay. Now, the standard deviation of uniform data is what? It's actually equal to b minus a squared over 12. Just a given, okay? We never derived this. They tell us we're not going to derive it for you. Just go ahead and use this, okay? So it's a matter of doing a few of these problems, and that's what this very problem is set up to give us, okay? So what did it end up being? It ended up being that 10 minus a over 12, that's squared. 10 minus a is 0. 10 minus 0 over 12 is 100 over 12, which ends up being, if you go back into the problem, you can calculate it right here, is just equal to 8.3 repeat. Okay, so it's 33333 all the way out there. That's everything we needed. See, we needed the standard deviation of the population, and that's it. That's the standard deviation of the population. Now, when we talk about the samples, we don't use the word standard deviation. Okay, we don't use that, so we don't get confused that we're talking about just a population and a sample, one sample of that population, like I talked about up above here, is no, we're talking about the variability of these samples. Okay, what ends up happening, we call this the standard error. We can actually calculate the standard deviation, and I'm going to show you here in a second. But what we need to understand is what the standard error is. So the minute that you see standard error, we can end up using that in the norm.dist formula, right? And what's that all about? Is we give it some information and it gives us back a probability. And when we're talking about sampling, we can, instead of the standard deviation as in the list here, we just substitute in the standard error in order to get at the results that we're looking for. So the point in this problem is we want to compare what happens to the standard error as our sample size goes from 50 to 100 to 250 to 500. Okay, so I quickly ran this out. Let's see if this ends up. So I ran this out for you. Okay, so here we have how many? 8 samples. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay, so here there are 8 samples. Samples 1 through sample 8 of size 50. Okay, so I labeled the tabs. This is the very data that was downloaded to us. Okay, so here's the data for n is equal to 50, and all that says is here's our 50 data points. Here's 100. Okay, and 250, and we do the same thing in each of them. Okay, and here is the standard deviation of the population I calculated. It's actually calculated in this. This is what you need to do. This is Okay, so this is the average of the averages. So the first thing you have to do is just simply average. Alt mu A is your keyboard shortcut in Windows. Okay, and so these are the averages down at the end here. Okay, of 50 numbers, and for each of the sheets, it's how many the samples are that we given, the sample size that we're given. We just do the average really fast here. We do the mean of these across the page here, and then this is the standard deviation of these numbers. These 8 numbers is that. And then finally, here's our standard error, which is equal to the population standard deviation divided by the square root, in this case, of 50. So it's 8.3 divided by the square root of 50, and that is our standard error. And if we do the same thing for each of these, when we go to 100, well, the square root of 100 is 10. So when we divide the normal distribution of the population here, okay, so now we end up with 8.3 divided by the square root of 100, which is divided by 10. So that just comes out like that. And then we did the same thing for 250. Okay, and you're going to notice as we go through here that the standard error goes down. Let's look at the numbers again. So you have to punch these numbers into the problem. Okay, so we started out with a standard error of 1.17, Then it went to 0.83. It's getting smaller and smaller. The more points you take, the standard error decreases. As the standard error decreases, the mean of our original problem was 5. Remember, it was a uniformly distributed data to begin with. But what happens is, as we take the samples, we look at the probability or the outcomes of what the samples are. Okay, they form a normal distribution. Okay, so now we're looking not at the underlying data. We're looking at, when we take samples, we look at the means of those samples, and we look at the probability is very close to 5. Okay, what it says is this might be the distribution where n is equal to 10, and then we went to 50, and then we went to 100, and every time we increase the sample size, this normal distribution of those sample means gets tighter and tighter. The more points you take, you're approximating the population more and more. And as you take a sample, if you have a very large number of, the sample size is very large, there's a lot of readings in there, is that the variability goes down. Okay, so this is the quizzical and interesting and useful part of when we sample, that the means that we're taking can follow a normal distribution, even if the underlying data was, say, uniform or even exponential or something else. Okay. And so we use this in industry. We use it all over the place for marketing. We use it for operations. We use it everywhere. The properties of this have been truly exploited. What we're doing is we're exploiting the usefulness of the math and the modeling that goes underneath this for many different kinds of problems. The next part of this problem says compare it to, it's along the lines of compare it to what's going on regarding a sample size of 10 all the way up to 500. Okay, and that this should lead you to the answer is that the variability, the standard error, is going down, down, down as we take more readings. That's the second part of the problem. So the third part of the problem talks about using the empirical model, which is basically, now this is the sampling distribution of the mean. Okay, when we take samples, we take the mean. That most likely it's going to come around centrally. The central tendency of it is to go toward the mean of the population, so we'll use that there. And it asks us what's the empirical model. We look at 5 plus or minus 3 standard errors. Okay, plus or minus 3 standard errors gives us the empirical model. We usually talk in terms of plus or minus 3 standard deviations or 3 standard errors here. So all we need to do is go ahead and compute that. I believe before I do that, I have to move this away. I think that causes me grief when I try to do this. So we need 5 is equal to 5. Let's go to the plus side here. Let's go to the minus side. Minus 3 times the standard error, like that. Okay, so our bracket is going to be, our error is so large with a sample of 50 at 1.1785 that the lower bracket is 1.46, and then the upper bracket is plus. The upper bracket we add, and that will come out to 8.5. Okay, and what you're going to notice is when we go out to 500, when you run your numbers, your standard error has gone down by what was it originally, 1.17. It's a quarter of the size, roughly a quarter to a third the size. So what that means is the empirical model will capture from -3 to 3 standard errors. That will capture your sample means is much tighter bracket. So you just go ahead and compute that, the lower and upper bracket, the way I just did here at 500 for sake of conversation is equal to, I'll do one of these, is equal to 5 minus 3 times the standard error. Okay, and here's a sampling distribution of our mean. in this case, when we have 500 samples, is 3.8. Our bracket starts at 3.8 and it goes to whatever it does. I'm just going to show you one side here. So we go back to where n is equal to 50. It was 1.46. Our sample means can vary from 5 down to 1.46 in general. This is a rough sketch of what's going on with our sampling means. This is what we're doing here. Whereas here it's 3.8. Okay, so it's much tighter. I mean, if we were to draw them over the same scale, it would look something like this. As our n goes up, then our variability goes down. For problem 6-7, we just went through doing the standard error here. So you can just go through this. This is not hard. It should not be hard compared to what we just did. We just ran through all these standard errors, so you should be able to calculate it for this one. Okay, for problem 6-9, now we're beginning to fly a little bit. You can use what's familiar to you. You should be able to be moving a little bit quicker here. Based upon extensive data from a national high school education testing program, the mean score of the national test scores for mathematics was found to be 614, and the standard deviation of national test scores for mathematics was found to be 204. We know we can use this to then use the sampling distribution of the mean. We can now find out what is the probability that a random sample of 289 students, there's your n, well, this is a nice real world problem, a nice uneven, a non-rounded number here. There's actual 289. What can often happen is you've done a survey or you're looking at something where you have imperfect survey results, so you're not going to get all your survey results or be even legit. But here we're looking at 289 students will have a mean score of more than 625. Remember, our mean was 614 and less than 604. So what that looks like, now this becomes a much more real world problem. All right. It's almost as though you get a kit when you get a problem like this. Okay. So it's like a kit. And you're going to be, so now we have the sampling distribution of the mean is a normal distribution like this. 614 is our mean. Always draw the picture because it is a picture and it's the best way to look at it. 625 and 604. So they want to know, have mean score more than 625. It's going to be somewhere up. I'm not even sure where it really is. It's 625 on this side. It wants to know what's the probability greater than 625, and then it wants to know less than 604. We can go back to using our norm.dist, but instead of using standard distribution, we use the standard error here. Okay, so so our standard, I had them waiting for us. The standard deviation was 204. Sample size was 289. The mean was 614. What's our standard error? Is just equal to our standard deviation over the square root of the sample size. Okay. Standard error is about 12. Let's see if that has more precision to it. Nope, comes out exactly 12. Okay. And then we're going to use our norm.dist to punch this in. I'm just going to write it here. It takes too long to actually punch it in. Norm.dist. Point of interest. The first one was 625. Okay. The mean we have was 614. Now we're going to use the standard error. Okay, so now we need the standard error here is 12 true. Okay. And we will get that number, but that will give us the probability up to and including this. So we need to do a 1 minus that, right? We want this. So we need 1 minus this probability. Okay. Whereas when we do the second part here, we're going to do the same thing. 604 And we don't have to do the 1 minus because we want this here. Okay. Now, what's the logical next step? They don't ask about it is, but what's the probability that a sample mean is going to be between 604 and 625? They don't ask that question here, but more often than not, you want to know usually what's say in the middle here. Okay, but we have the mechanics, we have the experience of using norm.dist from just simple distributions. Here we're using the sampling distribution of the mean, and I keep using that over and over again because you remember we have to just keep remembering we're doing sampling here, and we end up using the standard error, not the standard deviation. And problem 11 is some more practice. So doing exactly what we've done before there, and this puts some nice reality behind it. What is the distribution of the mean MPG for the sample? What is the probability the mean will be greater than? What is the probability that the mean of the sample will be less than? Same type of problem as the previous problem. Okay, so the next step here has to do with confidence intervals. Where can we take this? This discussion has to do with the third edition of Evans' book around page 231. So you need to read the text, and then this is to augment what is in the text there. So for a sample of 38 graduate students, okay, so our n is equal, we can write this down right away. If I can get it to work, draw. Sometimes it stalls here. Okay, so it's n is equal to 38. The average number of months of work experience for an MBA student was 33.87. The national deviation is known to be 20 months. Okay, so for data that's been collected over a long period of time, you will have a standard deviation of the population. The point here is you often don't have that. So, what is the 90% confidence interval for the population mean? So, what that looks like is this. Remember, this is the sampling distribution of the mean. Okay, so we're taking samples of this. What's the 90% confidence interval? That's saying we use this concept of alpha. Okay, we have a normal distribution like so. Okay, and we have alpha. That doesn't look like an alpha. We have an alpha of a half here and an alpha of a half here. Okay, so alpha is equal to 1 minus the probability or the confidence interval of 9.9. Okay, so there's point, what do we say? We're saying there's 5% chance here, the area under the curve here and the area under the curve here. Okay, so there's a 90% chance that the sample that we take contains the population mean. That's what we mean by 90, if we're talking about 90% here. 90% confidence interval means that there's a 90% chance that the true mean of the population is between some lower reference point and some upper reference point, and it already told us that the mean was 33.87. Okay, so a nice messy real world number there, 33.87 month. Okay, so there are three formula. One will be new here, and one is not. One is somewhat not heavily used so far, but we have used it plenty enough. But we'll get a better understanding of it. Our three equations are going to be: we have the norm.dist. We give it a point of interest. We give it a mean for a normal distribution. Pretty much always draw your normal distribution so you have an eye on what's really happening here. So we pick a point of interest here. Here's our mean. There's xi. Here's our mean. And we have some kind of standard deviation. Our data varies around the mean by some standard deviation, defined by standard deviation. We have true. This gives us a probability. Okay. Then we have the norm dot s dot inverse. Okay, this is what is going to become handy. It actually explains a few things here. Is what we do is we put in a probability here, and this pushes out a z. Okay, so if you think of the z table here, right? So this is the coarse. The coarse numbers come down and the finer numbers go across and you add them together. Okay, so our Z table has probabilities in here. These are all probabilities that relate to where the Z is. Okay, so we can slide the Z up and down the normal distribution anywhere from, if Z is equal to 0, that means we're right at the mean. Okay, to something that might be minus 3 standard deviations down there. Okay, Z equals minus 3. Just to remind us what's going on here is this norm.s.inverse goes in here, you give it the probability, and it returns the Z. It'll show you out here what Z you're using. Okay. And then finally, we're going to use a new formula here. The new formula is just going to wrap everything into these confidence interval type problems, and it is going to be, get that out of the way here. Confidence dot norm, okay, and you give it the alpha. In this case, it would be 0.10, the standard deviation, and the size, and the n. What's the sample size in here? So calculate it out for this problem. Confidence norm. It needs the alpha. In this case, it's 0.10. Standard deviation is 20, and the number of samples is 38. So this is going to give us the number that we add and subtract from the mean. Okay. So what's our confidence interval? The low end is going to be equal to 33.87. And there you have the confidence interval from 28.53 to 39.20 has a 90% chance likelihood of actually containing the mean. 90% of the time, so if you did this 100 times, 90 times you'll actually in your sample have captured what the mean of the population is. Okay, so this next problem here, 615, draw it out, write up what we know. Okay, so we have sample mean of 6.98. If you look down here, a survey of 21 college freshmen, average was 6.98 hours of sleep with a 90% interval, had a margin of error of 0.503. So here we're going to work backwards. They gave us the margin of error, and they give us a sample size here. So let's draw that. We have 6.98 is the mean number of hours that these freshmen were sleeping. Okay, so if we just subtract the margin of error is 0.503. Okay, so the first questions they want is we're going to do the low side and then the high side. Okay, so the low side is equal to 6.98 minus margin of error, and the upper side is going to be equal to, I could have just done this, plus margin of error is equal to that. Okay, so those are the two numbers that we've got. Be careful with, of course, as you put your answers into the system, it will tell you how many significant digits wants you to use here. So from 6.47 to 7.48 roughly. Okay, it says that we have a 90, when we did this sample of 21 students, we had a 90% chance of capturing the actual average of these freshmen, the population average. We have a 90% chance of, in this sample, capturing the mean of all the students there, all the freshmen. Okay, but now this is the tricky part. So I grabbed the equation, how we come up with, we use the confidence.norm in the previous example, and this is the underlying formula of what it is. Okay, so we have an average plus or minus half of z of half of alpha. Okay, so remember when we say 90%, alpha is going to be equal to 0.1, okay? And that says that this is where the errors will occur. There's a total of 10% split between 5% on the low side, 5% on the high side of not having captured the actual mean of the population. Okay, so that's why we take alpha. That's why alpha over 2. Okay, so that's all they're talking about whenever they see something like z of half of alpha. Okay, so what is z of that corresponds to 5%? Okay, how do we get that? We use the norm. Not too far. S dot inverse of a probability. So half of alpha is going to be 0.05. Okay, and that's going to give us this z of half alpha. Right? We're trying to find a z that corresponds to that. Okay, so let's punch that in there. That's not actually part of this problem, but I'm going through the steps here of understanding. 0.05. Okay, so that says that the z that corresponds to 5% down here on the low side is minus 1.64 standard deviation is down from the mean. Okay, just to give us an idea what corresponds to that. So now we know that our margin of error, 0.503, which is this portion here, right? Okay, so we can calculate that. So we can say that 0.503 is equal to this number up here, minus 1.64, times standard deviation divided by the square root of n. Okay, and we just solve for that. It's asking us what the population standard deviation was here, right? So that's this right here. Okay. So if we solve for that, it should be equal to sigma is equal to 0.503, that's this here, okay, star square root of 21 all of that divided by that number there. I just solved for this. I'm going to use parentheses, may not be needed here, but I always want to use parentheses so I don't trust the order of operations. Okay, one of the reasons for that is that it's not just you, but it's the person that comes after you, so that you can show exactly what's going on in these equations. And so it always takes a little bit of mental effort, maybe, as well as acuity, to be able to read equations without the parentheses in there and understand using the orders of operations. Okay, so if you're working on your own, it's okay to do shorthand, but otherwise you want to help everybody out. So it's going to be B6. I had to rewrite this in here. Okay, star the square root of 21 all over this number here. Okay, so you can see that we're using the error function here. This sigma divided by the square root of n. N is the sample. The sample size here is what really affects. We're scaling the straight value of a z alpha over 2. Okay, so the normal value would be minus 1.64, but we're scaling it by this factor here. We're degrading the sigma by dividing by square root of n. So this is the standard deviation of the population. Notice it's smaller. See, it's smaller. We have a wider variation when we have only a sample from the mean. That's the solution for that problem.